All right. That worked much better than me with the microphone, didn't it? Okay. Yeah, microphone. Okay. All right. I just want to say a couple things here. First of all, let's in the future all remember the calculator. Okay, you just need to be able to do basic calculations. Second thing is read the question, right? You guys are asking me for extra paper and doing all this work for question two row operations. You write the augmented matrix, you do an exchange, that's a row operation. You write down a matrix that has them ordered in a different order, and then you do one calculation to get the next matrix, and you're done. That's it. So make sure you read the question. Like, don't do a whole ton of work if it's not required. Okay, let's get going here. A couple things I'm going to say. One is we're going to finish this section today on Newton's method. We're going to see as a portion of extensions on Newton's method, the modified Newton's method, and we're also going to see the secant method. Then we're finished with root finding. We have our methods: bisection, fixed point iteration, Newton's method, as we're going to see, modified Newton's method, and secant method. That's how we're going to find roots. Then we're starting polynomial interpolation. Actually, a really fundamental topic. This is how do we put polynomials through points? That's basically the question. We're going to spend, I don't know, several lectures on this, on how to do this. And this is something that is used all of the time. I am, because Monday is a holiday, I am going to, probably tomorrow morning, I am going to record all of the section 3.1 lecture, and I'm going to post it to YouTube. And when we come back on Wednesday, I'm going to want you guys to watch that, and then I'm going to answer some questions about that, and then I'm going to move on to 3.3. Okay, so we'll have a full recording. Also, section 3.1 is the last section that will be on the midterm. The midterm will be everything up that we've done so far, all the sections we've done so far, plus 3.1, which we'll have a full recording for as of tomorrow at noon sometime. Okay, and then the midterm is the following week. Okay, all right. We were here talking about the fact that Newton's method converges quadratically, which is better than the bisection method, which converges linearly. And we can see that. You guys can see that. Please go into Canvas and run these demos, for which I'm making these little hand drawings. And if you choose the starting condition nicely, for Newton's method is actually performing a little bit worse than the bisection method, and then it overtakes it and what we call waterfalls. If you have a poor choice for your starting value, like your starting value is far away from the actual root, then the bisection method does what it always does. It just kind of plods down and finds you the answer nice and robustly. Newton's method will be much slower off the outset, and then some point it'll get close enough, and then it will, well, maybe not quite that dramatically steeply, it will waterfall. So this is why you'll see in the MATLAB documentation saying, well, maybe using bisection until we squish down the interval a little bit and we're close, and then we can switch over to Newton's method. Okay, so Newton's method does depend on a sort of a good initial guess, sometimes obtained by bisection. Yep, and if you're far away, you get very slow convergence, and then it waterfalls. And that happens, the waterfall happens when the derivative is large. Bisection is less sensitive, to the initial choices, and it typically requires 50 iterations to get to machine epsilon. And that's because you half the interval each time. So what happens? Each iteration, this is bisection. You gain okay, let's not do each iteration because I have to make a fraction. Every 3.3 iterations equals one significant figure. Okay, so if you accidentally start with, you start with twice the size interval, you only need one iteration to catch back up, right? It's a happy problem. So that's the bisection. You typically can get to machine epsilon in approximately 50 iterations. Okay, we didn't talk yet, and this is a bit of a, it's going to take me a little bit of time to go through the derivation on this, but we didn't consider the situation when we have a multiple root. So what we're going to do is identify what is a multiple root, and then how to recognize it, and then how to potentially compensate for this. So we have quadratic convergence when the derivative is not zero. We just saw that. But let's take a look at this function here as an example. This simple function there. It has a root at 0. But it is also the case that the derivative is also 0 at the root. And in fact, the second derivative is also 0 at the root. And then the third derivative is no longer 0 at the root. So at x equals 0, the root that you're trying to find, both the first and second derivative is 0 there. Okay, so we then have a, we want to identify this situation where we say here the root has multiplicity of 3. You can think like every polynomial has the degree n number of roots. So every cubic has 3 roots. And if it is like this, doesn't have 3 distinct roots, we say that it has one root with a multiplicity of 3. That's what this is telling you. A function that is continuous on its first m derivatives has a 0 of multiplicity m if the first m minus 1 derivatives are 0, but the mth one is not. That's exactly what we saw here. You'll notice the third derivative is not 0, and you'll notice that this thing has a root of multiplicity 3. That situation does not work as well when you run a Newton's method. So here's an experimental demonstration of that produced by MATLAB. So we consider this function here, e of x minus the m minus first Taylor polynomial for e of x. Why are we doing that? Well, because this function right here, this one here, which is looking what we'd expect, e of x minus 1, there, that function, that one has a, okay, so let's just put on the side here what that function is. F of x, if f of x is this, e of x minus 1, f of 0 is e to the 0 minus 1, and that's 0. So it has a 0, and then let's take a look at the derivative of it, f prime at x, that's going to be e to the x. That's never equal to 0. Okay, and not only is it not equal to 0 for any x, but it's certainly not 0 at 0, which is what we care about. So we see the convergence of Newton's method there. That is a simple root. Newton's method converging nicely. Now we take the next version of this function, that is this one here, f of x, well, let's not call it f of x as well, let's call it g of x. G of x is e to the x minus 1 minus x.
Okay, so if g of x is this guy here, e to the x minus 1 minus x, g of 0 is 0, e to the 0 is 1, and it says g of 0 is 0. There is a root at 0, and that's what you're trying to find. But g prime of x is e to the x minus 1. And that means that g prime of 0 is also 0. And in this case, g double prime of 0 is not 0. So now we have a root of a multiplicity 2. And you see what happens to the convergence. It's the red line. It's not converging anywhere near as quickly. So this number down here, whatever it is, 10 to the minus 15 or 16, right here, this is machine epsilon. Not going to get any better than that. So and then if you look, you can see it's getting worse. So there's the function. This function here is e to the x minus 1 minus x squared over 2. That one has a 0 of multiplicity 3. Multiplicity of the 0 at 0 is 3, and it converges even more slowly. Okay, that's the whole message here. It matters what the value of the derivative is at the root. If this happens, we can use a modified Newton's method in order to restore the quadratic convergence. Let's see how that works. One way to handle multiple roots, the modified Newton's method. Okay, so now we have a theorem. If a function has a 0 of multiplicity m, that will be true if and only if there's another, the function multiplied by x minus p to that multiplicity is not 0. Okay. I have an example. I don't have an example of that written down here. Let me just give you an example. Zero. That has a 0 of multiplicity 2 at 2. So what I'm saying is I can write this function f of x as x minus 2 squared times q of x. And I can take that multiplicity of that root at 0 out, and this thing is not 0 at the root. It doesn't have to be this straightforward. It doesn't have to be this easy to separate out. The root can look not like a polynomial. This is an example. You can multiply by the 0. You can factor the 0 out. Okay. All right, so we're going to use this to make this derivation of a modified Newton's method. I have a function here, mu of x. Mu of x is going to be f of x over. Okay. F of p is 0 implies that q of p. We're operating under the usual Newton's method thing. This is the case. X equals p is a simple root. Because at this point, f prime of x cannot be 0, otherwise you can't. Well, mu of x doesn't make sense. Okay, so we can apply that theorem here, and that means mu of x can be written as x minus p to the m times q of x. That's f of x divided by f prime of x. Now I'm taking the derivative of f of x. I get m x minus p to the m minus 1 q of x plus x minus p to the m p prime of x. Okay. I'm using the theorem to say that f of x can be written, I can factor out its root. So I substituted that in for f of x, then I took the derivative, f prime of x, and I put that there. Okay, I can simplify that. X minus p of x over m p of x plus x minus p. And I'm going to identify this piece here, and I'm going to call that q tilde. X minus p. Is q tilde of x um, 0? Yes or no? Yes or no? No, it's not. It is not. It is not because q of e is not 0. Okay, so therefore, this is a simple root situation. Therefore, by that theorem, p is a simple root of mu. That is because I have factored out this thing here. It's x minus p. I have that the other part, it does not have a 0, so it is a simple root. That's the theorem that's finding what is a simple root. Now what I can do is apply Newton's method. You will not have to replicate the derivation of this. You'll just need to understand that why we're modifying this and what the result is. Oh, sorry. Yeah, you're right. Here, I was starting here, and I'm starting here. Well, thank you for noticing that. Right, that was here. If this is 0, then this is 0, so long as this is not 0. Okay, so now we're going to apply Newton's method to mu of x. And what is Newton's method? That looks like this. The nth estimate to the root is the n minus first estimate to the root, mu at that's Newton's method. So let us now compute what is mu prime of x. Well, mu prime of x is the derivative with respect to x of f of x over f prime of x. That is what mu of x is. So I do that using the quotient rule, and I get f prime of x squared minus f of x f prime of x divided by all right. I can now substitute all of this stuff in here. I know what is mu of x. I know what is mu prime of x. I know the n on the first iteration zeros. I plug that back in, and I get a new formula. Here it is, the modified Newton's formula. I was writing this out. I'm thinking about this at this point. What I do is I will send you something prior to the midterm that says, I will have this on the screen during the class. Right? A sheet of paper like that. We'll have that. We'll do a similar thing for the final exam. So that, and that way everybody's not going to come in with a different sheet of paper and it's all scribbled all over the place and we try to copy the entire textbook down an extra micro print, right? That kind of thing. So we'll do it that way. But I don't want you to think to yourself, oh no, how am I going to remember that? That's the point. This is the modified Newton's method formula. The thing to notice here is it was a little bit more complicated. So it restores the quadratic convergence, but of course in each iteration you do have to do a few more calculations. You also now need to compute the second derivative of your function, which you didn't need from before. So there's some pluses to this, but there are some negatives as well. So there it is. We had the function from before. This guy, this is the same function on both of these graphs, but it's a little bit smaller over here. It's e to the x minus 1 minus x. And this is the regular Newton method. We saw that because it had a now that we've got the modified Newton's method, we see that the quadratic convergence here is restored. Okay. That's good news. It's much faster. I have to do way less iterations. I'm at like 5 iterations there. Instead, I'm down here in 5 iterations with the modified Newton on this thing. And over here, I'm not done. And it's been 20 iterations. Quadratic convergence is a lot faster than linear. Okay. Now, however, once we get roots of higher multiplicity, we have to make a lot more calculations. So we can see this is a graph of the error versus the number of iterations. The error being the distance between your latest estimate of the root and what the root actually is. And you can see what's happening. You're getting convergence. In this case, in the root case, you're getting convergence right down to machine epsilon. And then when you're looking at functions that are with multiplicity, you're getting like this. You get quick convergence, but then you do not get down to machine epsilon. If you can't fix this problem, you just keep doing more and more iterations and you don't get anywhere. So it's the modified Newton's method. I'm just going to write this. Modified Newton is not, or maybe say much less. Much less robust round-off error. That's because you're making a lot more calculations. Right. So not really a failure of the method. It's actually, I mean, it is a failure in the sense that you can't get as accurate, but it happens in general. Any general will find it tool. Okay, that's modified. Are there comments about this? Like that? Nothing. Okay. All right. So let's just get a summary on that. Summary is that second order Taylor expansion. That's why there's that quadratic there. It converges, provided you're sufficiently close. It converges as quadratic so long as the derivative is not zero at the root. When it's a double root, the convergence retreats back to being linear, and then you can restore that the modified Newton's method, but okay. Next thing I want to say, and I'm going to refer you to a video I'm going to produce for you, but I wanted to say something else which we haven't handled yet, and that is the secant method. Okay, so let's just observe. And I think the answer to that is really, I actually don't know. Okay, so I'm going to just say a couple things about the secant method, and then I'm going to send you an announcement with some instructions tomorrow. Okay, so what is the downside? So let's take a look at Newton's method. Newton's method is this P of n is P of n minus 1 minus f at P of n minus 1 divided by f prime. That is our Newton's method iteration formula. Okay, Newton's method is better than the bisection method in general, but you have this problem here of computing the derivative. Let's just talk about computing the derivative. We have a function. So if we want to compute the derivative at this point, we're going to be having to think about doing this. Either we have a formula for it for some reason, or we have to think about doing it symbolically, or we have to think about doing it numerically. And if we're going to write a general purpose routine where people are just going to be passing us functions, the computing of the derivative actually might be a serious obstacle. Okay? So the derivative computes the tangent line here. So let us just say this was our first guess in our Newton method. Here. You see where the root is? The root is right here. Our Newton method would provide this, in fact. Right here. That's the second step, right? Instead of okay, that's it. Right. So the idea would be instead of here, let me get a different color so I can try to show this in the diagram. Instead of there's my initial guess P naught. So I could do one of a couple of things, but one thing I could do is here's the number here, F of P naught. I could just move a little way on either side, or I could move halfway on both sides. Any which way, I'm basically going to go onto the function a small distance away, and let me just call that F of P naught, say, plus H. And instead of using the tangent line, I'm going to calculate the slope of the secant line. That was called the secant line. It's an approximation of the tangent. So that line is going to be somewhere here. So I'm just going to take 2 points, and then that slope is going to be f of p naught plus h minus f of p naught over h. Of course, when h goes to 0, then you have the definition. So what I do is oh, that's right, exactly. So that is a really good observation. In fact, that is more important than the formulas. These are the sort of things you want to be thinking about, right? And you're totally correct. So what's the problem here? First of all, you have potentially have cancellation error. That if these are very close in numbers, and then you're dividing by a small number, you get amplification of round off error. So calculating the secant slope there might be, but then again, if you take it too large, like in this case, took the value here, and I don't know, you took it really large, and you took it over on this side like that, and then you said, where's the secant line? That is actually good news in this case because you'd actually get closer. But your secant line does not cross the secant line. So indeed, that is a trade-off right there. But the upside is that you do not have to know symbolically the derivative, and or you don't have to make numeric calculation. The derivative only have to make function evaluations. Final statement I'm going to make about this is that we get this situation right here. We get that in terms of speed, we get the bisection method, and then we get the secant method, which is going to be better, but not quite as good as Newton's method, because our tangent line is a now approximation. So we get an ordinary okay, we are going to come back on Wednesday. And I'm going to send you an announcement of something I want you to watch before we come back. Okay. Can you send me an email? Not, no.
I don't know if you heard this already. Yeah, just like. Oh, I see.
Yeah. I have had a huge. Let me just.